Good evening. I want to begin with a very interesting discovery that's just been made. We've done several programs about the supernova that burst out in the large cloud of Magellan in 1987. At least that's when we saw it. It's 170,000 light years away. And there's a picture of it, actually taken from South Africa, and you can see that the supernova, near the bottom of the picture, is really bright. It's faded away now. Now, when supernovae die, and they represent the death of a very massive star, they may produce either black holes, or a supernova may turn into a pulsar, a super-dense, rapidly rotating neutron star sending out pulsed radio waves. And no one knew what this one was going to do. And now we know. It has become a pulsar, and a binary pulsar at that. The observations were made over in Chile at the Cerro Tololo Observatory, and there's a picture of the main dome there that I actually took a few weeks ago. And the telescope itself is one of the world's largest. It's a 4-meter reflector. Well, this is really very important indeed, because for the first time we've witnessed the birth of a pulsar, and that confirms all our theories about them. There have been 2 pulsars previously identified optically, one in the famous Crab Nebula, and the other in the southern constellation of Vela. And co-discoverer of both was Professor Mike Disney of Cardiff, and we're delighted that he joined us now. Mike, welcome to the Sky at Night.
Thank you, Patrick.
I imagine you're pretty excited about this pulsar.
Very excited, yes. I think we're going to have a ringside seat over the next few months or something we never could have hoped for.
Well, we still don't know really quite what's going to happen next, and rather than go into a long discussion now, I think it's probably better to wait until we do know. And so for our next Sky at Night programme, next month, we will deal with this new pulsar in detail. Meanwhile, on with the rest of our programme. You know, things are not always what they seem. The Victorian astronomers got a lot of things right. They also got a lot of things wrong. And in particular, they believe that most of the stars you can see at night time are a great deal more luminous than our sun, perhaps by a factor of 1,000 or so. Well, it's quite true that there are many naked-eye stars that are a great deal more brilliant than our sun. On the other hand, we now know that the Victorians are misled by what we call observational selection. They were seeing the bright stars because they really are bright, really luminous, and they missed many of the faint ones because obviously they weren't so noticeable. Well, that may apply also to galaxies. What about galaxies? Our Milky Way is powerful as a galaxy, and here's a lovely galaxy in the constellation of Hydra, Messier 83. But we tend to see the bright galaxies. And can there be observational selection there too, so that there may be more very faint galaxies than we thought? Now, very new evidence indicates that this is actually so. And so far as the galaxy population is concerned, we may be seeing only the tip of the iceberg, so to speak, and missing the crouching giants underneath. And there may be many galaxies which we have so far missed. So there could be a lot of observational selection there. And Mike, you've done a lot of work on this. What about observational selection in galaxies?
Well, Patrick, I think that it could be a lot more dramatic in the case of galaxies than in the case of stars, because there are 3 separate effects could be operating. First of all, galaxies could be, many of them, too faint to see easily, like as in the case of the stars and the Victorian astronomers. Secondly, some galaxies could be so tightly bound together, they could have such a high surface brightness that they could be confused with stars. And here's an example of one. You can see a star with spikes on it just below the right of the middle of the screen, and then just above it you see an object that is actually a galaxy.
This, of course, is the negative, the black and white.
That's right, it's a negative black and white. And unless we look very carefully, we would never have known that that was a galaxy at all. And lastly, you've got the opposite effect, where the galaxies spread out over the sky so much, like the next one, that you can hardly see its contrast with the background. See, it's a very, very diffuse smudge in the middle of the picture. It's hardly noticeable. It's just noticeable if you take a lot of care to look for it. And this could make such galaxies very difficult to see against our own sky, which of course is not absolutely dark. We live in a bright galaxy ourselves, a big spiral galaxy. We live in a spiral arm of it. We've got lots of bright stars around us. And so we're rather like somebody living in a lighted room who's looking out through the window at night, and all they can see are the other lighted rooms or the lights. And most of what's outside there we could easily be missing. We have to remember that only about 1% of the light that comes to us even on a dark site, on a dark night, is coming from the outside universe.
Well, is there any evidence for galaxies we can't actually see?
Well, there's some very interesting circumstantial evidence. Let's have a look at a calculation that we made at Cardiff of how easy it would be to observe galaxies of different sorts of surface brightness. And we see you get a very, very sharp peaked curve like this. Galaxies that were on the left-hand side of that diagram, ones which had a very high surface brightness, would look rather like that star-like galaxy we can see in the middle that we were looking at a minute ago. And galaxies that were too far to the right would look like these smudges that we also looked at. Now, if we look at the galaxies that we actually see, all the well-known ones that everyone's familiar with, the number observed, we get this amazing coincidence between the ones that are observed and the ease of observability. And that tells us that one of two things is going on. Either the good Lord has kindly organized all these galaxies so that they look just nice for us to observe most easily, or, as we believe in Cardiff is more likely, actually the universe is stuffed full of galaxies, and that so far we've only just been touching on the full population. We've only been seeing the easy-to-see ones. We can illustrate this by a little visual sequence. We've got a galaxy, an imaginary galaxy here now. We're going to play around with it a bit. It looks like, almost like a star. It actually contains, let's say, 1 billion stars. Now, it's hard to distinguish in this case from one of the stars. Mm-hmm. Now, let's spread it out a bit and see what happens. It begins to look like an ordinary galaxy of the kind that we're all familiar with. If we spread it out even more, though, it begins to stretch out in such a diffuse cloud that one can hardly distinguish its contrast against the background. And that could be a real problem. We could be missing all these galaxies that are not just the right concentration.
Well, it's very nice circumstantial evidence, but it is circumstantial only. What about direct evidence?
In order to find galaxies that nobody's seen before, you've got to look with a new technique. Now, what we've been doing is using a wonderful machine called the automatic plate measuring machine that was built at Cambridge a few years ago by Ed Kibblewhite. What that does is it scans a photographic plate with a laser beam. It stores all the information from that photographic plate inside a computer. And here we can see one branch of the Starlink computer network, and we can send these images from one branch to another one, for example, down to Cardiff, where we can do all sorts of massaging of that image to bring out things that one wouldn't have seen normally.
Well, what are you finding?
Well, we've concentrated and made a very deep search in a particular cluster of galaxies in Fornax in the southern hemisphere. Now, if we look at this next slide, we'll see the cluster in negative once again, and you can see the big black blobs are ordinary galaxies of the sort we're familiar with. We've also found there's at least 1,700 other objects on that plate alone, which people weren't really aware of before. For example, if we look up in the top right, we'll see a tiny little thing there. If we blow it up, we see it really is an extended galaxy of some sort in the background. And if we look again in the middle of the frame, we see another such object. And again, if we blow it up, we can just see that it's stretched out and that it's actually a galaxy. So there's an awful lot of those on the plate. And from those objects, we've managed to make 3 very interesting discoveries or observations. First of all, there are lots and lots of these low surface brightness objects. For example, we can look at 3 of them now. There's one in the middle of the screen that's quite clearly a galaxy. If we go on a stage further to the next one, we see another one that's a smudge now, slightly below the middle.
Only just see it.
You can only just see it, and there's another galaxy beside it to show it more easily, and there is just about the limit of what we could possibly detect. And that's after a good deal of work with the computer massaging the images. So that's the first thing, that there are a lot of those galaxies, low surface brightness galaxies, and they're not all insignificant dwarf galaxies. For example, last year, David Malin, working in the Virgo cluster, was looking at a little object at the top left-hand side here that's hardly distinguishable for a star, but when he did some photographic magic on it, he discovered that in fact it was really a big, bright object stretched out in the sky. And when it was looked at with a very large telescope to measure its distance, it was found it was enormous distance away. that it is about 100 times the size of our own Milky Way in area, and that it contains no less than 10 times as many stars as our Milky Way.
It really is a huge galaxy. Distance, 2,500 million light years, something like that?
Something like that, yes.
So it really is a huge thing. Well, if there are large numbers of these very low surface brightness galaxies that we haven't known about before, well, they could cover a lot of the sky.
Yes, indeed, they could, Patrick, and they could provide a rather serious blocking effect on the background universe. For example, if we look at this next sequence, we've got an observer on the left, we've got a schematic galaxy drawn in the middle, and on the right, well, let's say we've got a distant quasar at the end of the universe. Now, that quasar we can see, that's indicated by the ray of light coming into the observer's eye, but supposing we had a second quasar now, whose light was coming through the edge of that galaxy, the light would be affected and slightly blocked. And if, of course, it was lying behind the center of the galaxy, then we wouldn't see it at all. Now, we know that if we look at quasar spectra, as in this next sequence here, we'll see an object which you can see the spectrum, that's to say the light, coming from it as a function of color, and you can see little dips in the spectrum. For example, there's one near the middle, and there's one on the right-hand side. And these are telling us that there's something in the way of this quasar blocking it off. Now, it couldn't be an ordinary galaxy because there's far too many of them. It's possible, indeed probable, it seems to us, that some of these, quite a large number of these, are actually iceberg galaxies in the foreground.
Now, what about the other galaxies, the compact ones, those that are so easily mistaken for stars?
Yes, so this is something we've only been able to do recently. You couldn't possibly do this with the naked eye. It would be far too tedious. You've got to look at 100,000 stars and then see which small number of these are not actually stars at all. They're galaxies that are just slightly different from stars in appearance. For example, here's one here. You can see the object in the middle is actually a galaxy. It doesn't have the sort of spikes on that we see on stars as a result of our optics. Now, the APM machine, the plate measuring machine we were talking about, can look at 100,000 stars on a plate at once, and it can quickly distinguish which of those are not stars but are actually nuclear galaxies. And we've been looking at some of those recently. We found quite a lot on the plates. We know that some of them are very distant luminous objects, rather like Seyfert galaxy-type quasar-like galaxies, and some of them are almost certainly in the foreground. They're faint galaxies squeezed together very tightly.
And what does that tell you about the galaxies themselves?
Well, there's something else we have to look at, and that is also that we've also discovered that ordinary spiral galaxies, there's something funny going on there. If we think of the ordinary spiral galaxy we saw earlier on, here's a picture of another one, and you can see that the image is affected by little black clouds all over it.
Yes, indeed.
This means that some of the light is almost certainly being absorbed by clouds of smoke and gas inside the galaxy.
Well, we'd always thought more that before now that galaxies were more or less transparent.
Indeed we did. And what we've now done at Cardiff is we've made some models in a computer of galaxies. We put in dust and we put in smoke. And we found, first of all, that they look just like the galaxies we all know and love. They're not affected by, they're not obviously affected by this smoke and dust. And yet, this smoke and dust would have just the effect we observe, which is that there are not very many high surface brightness. We never see very high surface brightness spiral galaxies, because we don't see, what we're looking at, we think, is the upper surface of the galaxy. We're only seeing the unobscured stars. All the other stars underneath are hidden below our sight and we don't see them. And so galaxies could actually be very much affected by smoke and dust, and they're very different to what we thought. For instance, they could contain a lot more light than we thought. They could contain a lot more stars than we thought. And they could explain, this dust and smoke could explain the infrared observations that have been made in recent years with the IRAS satellite. And perhaps most interesting, if they really are all opaque so we can't see them, they could be blocking off the distant universe. They could prevent us from seeing quasars beyond a redshift of 4, which, as you know, we've failed to find very many of those. And also they could be hiding from our sight the process of galaxy formation taking place in the distance.
Well, if there are so many of these galaxies of various types, can there be any kind of an upper limit to the number of galaxies that we can actually observe or we can detect in any way?
Yes, there definitely must be an upper limit. We can't stuff so many galaxies into the universe that the whole sky would glow. We know from observations that only about 1% of the light that's reaching us, even here on Earth, only 1% of it could come from the most distant parts of the universe. And so that means we can only put in between, at the most, 5 and 10 times as much galaxy light as we already know about.
Well, what comes next in this research?
Well, I think we've done everything that one could hope to do with a photographic process. From now on, we've got to go one step further in technology. We've got to build extremely sensitive television cameras with a wide field of view. We've got to put them on large telescopes, and we've got to look at a large area of sky. And that's what we've been doing. We're building jointly with Craig Mackay in Cambridge, we're building a camera which we're going to call, after your very neat suggestion, the Hitchhiker, and we're going to put it on the William Herschel telescope. This is our new telescope in La Palma Observatory in the Canaries, and about a year from now, every night that that telescope's operating, our Hitchhiker camera will, as it were, be looking over the astronomer's shoulder and looking at the universe with much greater depth than it's been looked at before. We'll be getting 20 deep frames every night of the sky, and we'll be looking for very, very low surface brightness objects of the sort we couldn't have even seen on the deepest photographic plates.
Well, it looks to me very much as though the results of this new kind of research indicates that there may be a great deal more mass detectable in the universe than we have been able to detect before. And that could, I suppose, indicate that the universe could be closed and not open, that the present expansion won't continue indefinitely.
Yes, I think that's a very exciting question. I wouldn't be prepared to put very much money on the answer at the moment, but certainly every time one discovers new types of galaxies, larger numbers of them, one's increasing the amount of mass in space, one's increasing the likelihood that the universe is closed and finite.
What about the Hubble Space Telescope? What's that going to tell us if it goes up at the end of the year?
Well, this is one of the things that we're all hoping we can measure with the Space Telescope. We're hoping that we'll be able to make, in some sense, a measurement of whether the universe is finite or not. We'll have to see.
Well, I wonder. And within a few months now, we may know a great deal more. Mike, thank you very much. So you see, there's still a great deal to learn. But meanwhile, for our next program, we're going to come back to something a bit nearer home, only 170,000 light years away, and give you what we hope is a full report upon what is happening to the new pulsar in the Large Cloud of Magellan. For the meantime, from Mike and myself, good night.
And that next programme will be shown on BBC One Scotland on Sunday the 12th of March. The one you've just seen will be shown again at 4:30 on Saturday afternoon on BBC Two.